Welcome to the training session titled Marine and Polar Mesolows. My name is Dan Bikus. Ed Zoke assisted me in putting this together. Our learning objective is to learn how to make optimal use of GOES16 and 17 capabilities for identification of marine and polar mesolows. Mesolow, which is sometimes referred to as a polar low, is defined as a small but fairly intense low in maritime regions. They exist in cold air outbreaks, where cold air advects over relatively warm water. Potential hazardous weather associated with mesolows includes convection that can lead to heavy precipitation and also icing and turbulence, also low visibility and strong winds. Our case is from 12 March 2017. We begin with a GOES16 IR image overlay with METARs and 850 millibar plots. Cold air is flowing over the relatively warm Great Lakes. There are lake effect snowbands clearly evident over Lake Superior. However, our primary focus is the existence of this mesolow over southern Lake Michigan. Note from the METARs that temperatures are in the mid-teens. Surface winds are light, which favors the development of a mesolow. We'll start our analysis of the mesolow over Lake Michigan with the most familiar channel, which is the visible band at 0.64 microns. During daytime, this band is ideal since it's the highest resolution band possible at ½ kilometer and depicts low-level clouds associated with the mesolow clearly. So long as there are no high clouds obscuring what is happening at low levels, you can see flare-ups in the convection, say on the southeast flank over here, around the mesolow, and these may be associated with localized heavy snow. Also note the relatively fast-moving clouds on the western flank of the mesolow at times. These can be associated with localized strong winds. GOES imagery is useful in tracking the mesolow for potentially moving onshore, bringing potential for localized heavy precipitation, strong winds, and low visibility with it. Now let's compare GOES16 with GOES13, which was still the operational GOES East satellite at this time. On the left we have our GOES16 visible and 10.3 IR band, and on the right we have our GOES13 visible and 10.7 micron IR band. There are some missing images in the loop, so focus on the superior spatial resolution of GOES16. In the previous GOES era, high clouds, in particular with the IR band, would have made mesolow identification much more difficult. With GOES16 and 17, not only do we have superior spatial and temporal resolution, but we also have additional bands, which can be quite useful for mesolow monitoring during daytime hours. On the bottom panels, we have the familiar visible band at 0.64 and the IR band at 10.3 microns to compare with the two new bands that we have in the top panels. So in the upper left we have the veggie band at 0.86 microns. This band shows greater contrast between land and water, therefore coastlines become less ambiguous and small islands are much easier to see. In the upper right is the 1.6 micron snow and ice band. This band is useful for delineating clouds from ice or snow cover. Snow and ice surfaces are strongly absorbing at this wavelength, so the reflectance is low, thus darker in this color table. However, cloud reflectance is high. This contrast helps delineate clouds from snow or ice cover. We don't have any ice cover in this example, however this band is also useful in capturing glaciation at cloud top. Clouds composed of supercooled water will appear bright, whereas clouds composed of ice will appear dark, since ice is strongly absorbing at this wavelength. Convective clouds that become deeper can be identified as darker in this band. This band is also commonly used in various RGB products to help identify cloud glaciation, as we'll discuss later. Time for an interactive exercise. In this 4-panel, we have the 3 GOES16 water vapor channels, 7.3 microns in the upper left, 6.9 in the upper right, and 6.2 in the lower left, along with the old GOES13 water vapor band in the lower right. Which panels can you see the mesolow? Also, why are you unable to see the mesolow in some of these panels? I'll give you some time to think about this before moving forward. Recall the earlier training module that's part of the satellite foundational course on the water vapor bands. The water vapor band that sees lowest in altitude is at 7.3 microns, while the band that sees the highest is at 6.2 microns. This is an application of knowledge of weighting function profiles for the various water vapor bands. A mesolow is a low-level feature, therefore it will show up the best at 7.3 microns and is unlikely to show up in the other two water vapor bands due to the weighting function profile being above the altitude of the clouds associated with the mesolow. This is also true for the old water vapor band at 6.5 microns, which would not have shown the mesolow even with the higher spatial resolution of GOES16. What about mesolow identification at night? We need to make use of IR bands. This loop shows the origins of the mesolow during the overnight hours in 3 IR bands, as well as an RGB product that makes use of those 3 IR bands. Let's start with the familiar 10.3 micron band in the upper left. The low-level clouds associated with the mesolow show up as these gray colors in the default IR color table, while high clouds are color enhanced. While it is not the case in this example, at times high clouds may make it difficult to identify the mesolow. In that situation, making use of an RGB product, such as the nighttime microphysics product, can help discriminate between the high clouds, which in this product show up as red, versus the low clouds associated with the mesolow, which in this product show up as these yellowish green colors. The 3.9 and 12.3 micron bands are shown at the bottom. Frequently the RGB provides more contrast to features than a single band image would alone. There are some RGB products for daytime use as well. This is the day cloud phase distinction RGB. High clouds are reddish yellow, while low clouds, such as with this mesolow, appear white. Clouds that undergo glaciation transition from white to green, since the 1.6 micron band absorbs ice, therefore it's darker and less blue with more green. The mesolow over Lake Michigan remains in the white colors throughout the loop, but this product can be useful to monitor for relatively deeper convection, which may indicate locally heavier snowfall, such as the green colors that we see across this lake effect snow band in southern Lake Huron. Snow on the ground and ice cover will appear green in this RGB composite. In order to better understand RGB products, make use of the AWIPS cursor readout on the RGB product and its components. Use this information along with the corresponding quick guide to understand why features appear certain colors. In summary, GOES16 and 17 aid in mesolow identification because of their greater spatial and temporal resolution compared to the previous GOES. The IR and visible bands will continue to play a prominent role in mesolow identification. However, there are new visible bands on GOES16 and 17 that aid in mesolow identification. This includes the 0.86 micron veggie band, which increases contrast between water and land, better identifying coastlines and islands. Also, the 1.6 micron band can easily discriminate between clouds and snow or ice cover. This is particularly important for mesolow identification against a typical winter background in cloud streamers over ice fields of unknown fractional coverage. RGB products are particularly well suited for shallow convection to discriminate the mesolow from ice and snow cover, and also make it easier to identify if partially obscured by high clouds. Be sure to make use of the 4-panel display to display multiple satellite bands in tandem for the most complete diagnosis, similar to multiple fields of dual-pole radar display. Finally, although the mesolow shown in this case study did not come ashore and cause hazardous weather, we post a link to a blog entry in the pre-GOES-R era of a relatively high-impact mesolow that came ashore to cause localized hazardous weather.